thanks to everybody for attending this webcast. I really appreciate that. And I sincerely hope that this material that you see today, maybe it's something new, and more importantly, hopefully something that you can use in your own job in the future. So with that, let's start. Each time you see a little light bulb and a tip symbol, the promise was that we'd give you 5 tips, and I think there's actually more than 5, but when that appears on one of the slides, I'll be commenting on how that in particular can hopefully help you in the work that you do. So first topic that I'd like to dive into to allow us to see some of the important details is it was really asking, what is measurement decision risk? So what I like to maybe ask you, unfortunately I won't be able to hear your reply, is why do you make measurements? And perhaps even more to the point, what do you do with the result of a measurement after you take one? So if we were live, I would wait until somebody said something, and I'm hoping that you're thinking about something. But I'd like to just ask you, do you compare that measurement result to some specification, a design specification if you're in R&D, or a customer specification if you're in production? And do you then make a pass or fail decision to ship or reject the item that you were testing? If that's what you're doing, the process by which you decide it's a pass or nope, it's a fail, that's called a decision rule. So I'm just going to use that term. It gets used in a lot of technical literature that you might not be familiar with, but I'm probably going to use it enough times that I wanted to just define it for you. So why are these decision rules important? So when you perform a measurement and you make a pass-fail statement, such as in and out of tolerance, there's really only 2 possible outcomes. So after I show you the first one, you're either right or you're wrong. So how do you know which one it is? Well, every measurement has an associated uncertainty with it. I'm going to talk more about that, but you can think of that as system errors. And it's that uncertainty that affects your chance of being right or wrong. Now, I'm a visual person, so those words don't mean that much to me. Oh, and I wanted to mention one other thing. Spoiler alert, there are no perfect measurements, okay? So the only way to really make sense of any measurement is, what did you measure, and how accurate was that measurement? So what I'd like to do is just sort of illustrate what I mean by this, and this drawing is from a good friend who's the chief corporate metrologist over at Fluke Corporation, Jeff Gust. And so what we've got drawn here is a 2-sided specification, a plus or minus, and then the actual measurement is the blue dot. So that's the only thing you really know, or that you have observed. Now then, what goes along with this is if you have estimated all the sources of errors in a measurement and put those into a standard deviation, and then, like a lot of things electronic, let's just say it's a Gaussian distribution of those errors. It isn't always, but frequently it is. Then if you were to go plus or minus 2 standard deviations, any of you with a statistics background would probably be able to say, oh, that ought to cover 95% of the cases. And that is correct. So that's what I'm trying to draw here. So if you were then asked to say, here's a measurement, you see an upper limit, is that in spec? Just about anybody would say, yeah, looks good. So now what I'd like to do is just show you, what about this case here? Now I made the same measurement in case B, but wow, look at this. It's quite a bit of that error possibility is outside of the specification. So the natural question that just about any of us would have, certainly any of our bosses, would be, what % risk is that? And so that's kind of what we're thinking here. Now I just want to show you one other thing. This is another friend of mine from Raytheon who said, you know, Bob, in PowerPoint you could show a distribution if you did it this way. So just like any Gaussian distribution, the most likely answer, true answer, is somewhere near the middle, but still there's a fair amount of shading in case B that's outside of our of the upper spec. Now, wouldn't it be nice if we could make an app for our phone for measurement where you could just simply look at it and say, oh, there's the percent risk? Because just about anybody, we all of us in our own personal life, you check a phone. Let's say you're going skiing. You want to know, is it going to snow, or do I need chains, whatever it might be. So you can see at the bottom there's the percent risk that it's, or there's the percent likelihood that it's either going to rain or snow or not, any of those things. And it varies around. And I want you to notice one other thing. You've probably never noticed this before, and I hadn't until I picked this out for a slide. But notice that the nearest resolution they're even showing here is 10%. So when I get to how do you estimate percent later, don't get hung up on needing 5 decimal places to the right of the or 5 digits to the right of the decimal. Here they're only showing plus or minus 10%, and that's still useful information for most of us to figure out if we're going to wear a raincoat or bring an umbrella or whatever. So now I'd like to dive into errors due to measurement risk. And when you look at this, you have a binary pass or fail, but really there's 4 states. And so I want to start with a verbal description. In this chart, on the top, left and right, that's the true state. Is it really good or is it bad? But all we can know is what we test. So the outcome of our measurement results, we either pass or fail it. So if it's good and we measure it as a pass, that's what you want to ship to customers. Likewise, if you measure it as bad or fail, and it truly is bad, that's unfortunate, but at least you're not shipping bad product to customers, and that's really what you're trying to screen for. So those are the 2 obvious things that we know happens, but you can see this has got 4 quadrants. If we fail something, if we measure it and it fails our test, but it was really good, then what happened was normally in the production process, you will recycle that around and try to adjust it or whatever it might be. So you're going to have a bunch of extra rework. If you're a production engineer, you're quite familiar with bone piles. And that is, when you finally give up, you have scrap costs. So that's an unfortunate one that you may be aware of. But perhaps the most insidious one of all is when you pass it, but really it was bad. And so what that will do is eventually increase your warranty costs and possibly could even affect your reputation. Now, I don't want to beat them up because they already suffered enough, but one of the very major suppliers of phones had an issue with lithium batteries, and it was an extremely low incidence. And that particular company is very careful about their testing. But still, you get the idea of how big a problem it can be if you have false accepts. So they can really be a problem. And obviously, in the aerospace defense area, if we have a warfighter out in Afghanistan or somewhere like that, and for something that we've done causes them to have significant problems, we can't have that. So, just a little talk about measurement uncertainty. Now, a lot of my time I spend in international standards, so that's the official term that gets used. And if you've never heard that, relax. But what you probably have heard of is test system accuracy. So I want to talk about that. How do you figure out accuracy? Now, this is one of the tips that I want to give you. there is an international guide called the Guide for Expression of Uncertainty of Measurements, and you can download it for free, and it'll just give you headaches, but it is the most official one. Or you can read this United Kingdom accreditation document, which is also a free download. All you have to do is put M3003 in any browser that's your favorite, and you can easily download the PDF. For anyone that's new to the topic of measurement uncertainty, this is my favorite reference. I highly recommend it, and one of the best things about it is they have good examples in here, so you can not only read about it, but you can get ideas and examples. So this is a great document. Sometimes I visit customers, and I always like to ask the question, how do you estimate system accuracy, like in a final test system or a test system that's used to transition from design to manufacturing? And usually what I get is a little bit of a blank look or a little embarrassed, and then I usually have to ask, is it tribal knowledge? And then everybody nods their head. So part of the tip here is, wouldn't you like to be the engineer who, rather than just relying on tribal knowledge, which may be good or maybe average, and allow your company to move forward and be using international standards? So I think you can really make a difference at your company and perhaps even in your career by thinking about system accuracy in terms of measurement uncertainty. To give you an example of how do you figure out what measurement uncertainty is, here there's an application note which is at the bottom, and I understand you'll have access to these slides. But when you make a power measurement with, say, a power sensor and a power meter, there are 9 different sources of error. They're not all the same, of course. They're different amounts, and I even have a little pie chart to show you that about half of these errors are mismatch. A little bit it goes into the meter, say instrumentation accuracy, and then the rest is in the sensor, primarily with the Cal factor uncertainty. So if you look at this, you can see there's a bunch of errors, and sometimes people say to me, wow, does Keysight keep track of all those when you're estimating the accuracy of an overall measurement? And certainly in our production test systems, I go, yeah. How else would you do it? So you might just think about this if you haven't already. That's a good app note. It's helpful. And this is an example of measurement uncertainty. I have sometimes in the past heard people tell me that they use test accuracy ratio. So I just want to do a little definition of terms here. Right now, I'd like to define for you test uncertainty ratio, which is you divide the tolerance, or you could say spec, by the measurement uncertainty. Okay, so you see a little definition here. It's the spec, and then normally what we mean by the uncertainty is the expanded measurement uncertainty, which is equal to 2 times the standard deviation that you come up with. Now, one thing you can notice is that the error or the uncertainty is in the denominator, and that means the more error you have, the lower the test uncertainty ratio will be. When I show you some curves coming up, you'll need to see this, so I wanted to show you this. But I do want to tell you, sometimes when I'm talking about uncertainty, people say, oh yeah, with the power meter, power measurements, I know that the instrumentation accuracy is 0.5% of reading. And I go, no. You cannot estimate divide the spec by just that one error. You won't get anywhere near what the real uncertainty is. You're completely ignoring, in this case, the mismatch. So when test accuracy ratio is you divide the spec by a single spec, and you have to look in a data sheet, or you have to consider loss in your cables or mismatch in switches in a measurement pad. You have to think of all of those. But there are times when you can actually use just a single specification, and this would be one of them. So here we have one of our calibration technicians measuring gauge blocks, which so precision length measurement. And notice she looks like she's dressed pretty warm, and she's even wearing gloves. And the gloves aren't because she's that cold. It's because it's really important to make these measurements at within a half a degree of 20 degrees Celsius. That's where all these official lengths are determined. And if you were to if you do temperature very, very, very carefully, you temperature soak all of the things you want to measure ahead of time. You have a room with a closed door, all that kind of stuff. If you do all the things to keep temperature not being an error, because it's the largest source of air, then the only real error that remains is how accurate were the reference samples that you got from NMI such as NIST. And so you can imagine that's a case where you can actually use just a single error. So now I'd like to talk about different kinds of risk. And first I'm going to talk about specific risk. I will define that momentarily. This is if you consider the errors of false accept or false reject, if you consider the effects, the errors in your test system only. So I mentioned before that if you think of the errors, it's probably going to come out as a probability density function. And even if you don't speak to statistics, and truth is I'm not the most knowledgeable about statistics either, but there's a distribution function, and if you want to understand what risk is, then you corresponding to a certain outcome, then what you have to do is integrate the area under the curve of interest. Now I have another document here. I didn't mark it as a tip, but it's the OIML G19, and that's another acronym for legal metrology. And this, if you enter OIML G19, this is another great reference. It's a little bit long, but it has a lot of great examples, and I highly recommend that document too, to go along with the other one. So let me just show you visually what it looks like. This is a decision roll. I'm gonna put, for this example, we have a case A and a case B, and in both cases the measurement is right at the specification. Well, if it was just a little bit above the specification, normally we'd say, okay, that's a fail. But if you ask yourself, what's the probability of false accept, you integrate the area above, under the curve above, and then you'd say, oh, well, I don't need to do a definite integral to tell you that under B, that's 50%. And similarly with A, it's more narrow, but the answer is still 50%. So that's why this one, when you have no guard band, is sometimes called zero guard band. Sometimes it's called the simple rule, and sometimes it's called shared risk. So you have this situation here. And it's shared because the false accept is, in literature, is oftentimes called consumer risk. So that's when we buy something, the likelihood that it was out of spec. They call that consumer risk. You can call it false accept. False reject is just the other side of the curve. And in this case, they're equal right at that point. Now, I want to just show you that when you have, in the case of my illustration here, I have smaller measurement uncertainty, therefore a higher test uncertainty ratio. And look what happens if I just give a little bit of guard band here. Then what you can see is that the area above the red line for A is quite a bit smaller than for B. So it just illustrates graphically that if you can keep your measurement uncertainty to a minimum, you're also going to reduce the false accept risk. Now, there are tables that you can use, so you don't have to perform the integration. And this is another bit from that OIML G19. So, I mean, you can look these things up. I thought that was interesting. It reminded me of logarithms from many years ago. But here's the one I like. My colleague John Harbin and I wrote a paper for NCSLI last year, and so what you can look at here is you can interpolate right off of a graph to get the specific risk. And you only need to know three things. You need to know what is the spec, or as we say, tolerance, what is the measurement uncertainty, and what did you measure. And then what you do to use this table is you simply divide the measurement value into the tolerance, and that gives you a percent of spec. That's the x-axis here. And then you divide the uncertainty into the tolerance, and that gives you the test uncertainty ratio. And I have one example here. Let's say you measured something and you were at 80% of the spec limit. If your test uncertainty ratio for this particular measurement is 4 to 1, then your specific risk is going to be 5%. 5% likelihood that you measured it passed, but it really didn't. If your test uncertainty ratio is only 2 to 1, notice that that goes up to 23%, almost 1 in 4. So these curves make it pretty easy for you to estimate. So where am I operating with specific risk? Oops, now I want to go back. Sorry, they told me to turn off. So now I'd like to go to an example. Oh, man. Hold on. We'll try one more time. Apparently, the slide that I gave everybody is hidden because you're supposed to get a howling siren there for a policeman pulling you over, and I'm truly irritated that you didn't get that. Sorry about that. But what I'd like to then show you is an example of specific risk. So if, oh, I know why, because it was on my computer, not here. Oh, well. So looking at specific risk, this comes right out of another document I'm about to recommend to you, but as one of their examples. So police radar guns have an uncertainty of about 2%. So the question then becomes, what is the speed that the policeman or woman must measure to ensure that the car is traveling greater than the speed limit, in this case 60 miles an hour, with a 99.9% probability? So it's a single-sided limit. You can look up in the statistics book for 99.9, you need 3.09 standard deviations. You put this into a little formula here, and it says that you have to be going 107 kilometers an hour, and that translates to 64 miles an hour for that. Now, I want to give you a bonus tip, and if you learn nothing else from today, this one might save you money or aggravation. I live in a state, California, where if you're more than 15 miles an hour over speed limit, which is usually 65, then the fine goes up big time, dramatically. So in a state where there's mountains and you're not paying attention coming down out of the hills, this can be a problem, as I happen to know personally. So if you have a policeman who pulls you over and says, I measured you at 80 miles an hour, 81, and you say, please, sir, could you write down 79 miles an hour, then I'll gladly admit that I was going faster than 65, but please don't put 80. If they insist on writing the 80, then you might want to keep a copy of this slide in your glove compartment, because they have to measure at least 85.3 miles an hour by the same formula to know with a 99.9% certainty that you were going more than 80. And you could take this to court and you could get off. So anyway, a helpful tip there. Now that was specific risk. Most of you and in fact, a lot of my own work, we use average risk. And so I want to define what that is and show you how that works. But what I would like to do is call your attention to this is another great document. This is the Bureau of Weights and Measures, which if I had any decent French I could pronounce, but it's the supreme authority for measurements is BIPM. They're located in France. Of course, this thing is in English too. And you can get this. It's really, really good. And if you're at all interested in understanding the measurement decision risk, this is the very best document. It's a bit of a hard read, and it took me several times. So, now that certain things are legal, it takes 3 times to get it, and this is definitely one of those. But you can either pay a bunch of Swiss francs and get the ISO guide version, or you can get the same thing for free and download it as JCGM 106. And it was published in 2012. Really a good document. Also want to mention that another colleague of mine from Keysight wrote a paper a couple years back, and you have the link to it here. The two of these together are really, really helpful for what we're talking about today. And what I want to call to your attention now is that when you're looking at average risk, that is really a joint probability density function. So it's a function both of the measurement process uncertainty, which was the only term on the right that we just looked at for specific risk, and it also includes the errors of or the distribution of the device population itself. So for instance, if something is good because of the first term and you measure it as out, it turns out that it's still good, right? So so it's a combination of both of these things that are involved. And so it ends up if you want to know the risk, you have to do a double integration over the area of interest. Now, most people can't visualize a double integration. So what I'm going to do is give you an example, and I'll show you some visual things that you can take from there. So that said, let's say we have a precision mass, and we want to say, okay, what is this thing? We have an error defined by what we measure minus the true value. So we don't really know what the true value is. That's what we're trying to estimate, but we can measure it, and this will be the official way to do that. So if you were to look at any manufactured item, in this case I'm just showing some precision masses, as they come off a production line, they're not all the same. And there's some specification, plus or minus some amount, that you're looking to verify, and that's where you want the true value. So some of them, most of them are in, sometimes they're not. So one way to understand what's going on is to do a Monte Carlo simulation. And so what I'm showing here is that on the x-axis is the range of the true values versus the range of what we can measure. And so if you're not already familiar with Monte Carlo analyses, what you do is you do a number of trials where you allow both or any of the variables, in this case we have 2, to vary randomly, and then each trial is a dot. So and then what you can do is you can say over the range, by the way, the lighter area in the middle is a higher concentration of trial dots. So we have the range of the true value, that's the customer specification, and then on the y-axis we have what we can measure. Well, if you measure something to pass, and in fact the true notion is that it did, that's great news. That's what we're all trying to send to our customers. And for any of those which are outside the limits that we've set, we fail those, and that's too bad that they failed, but at least we know we've correctly identified them and haven't shipped them to our customer. But as I told you before, these ones over here in the quadrant that you see now, each of these trials represents a false accept because we measured it to pass, but it wasn't good. And so what I can tell you is if you solve some of those equations, if you have test uncertainty ratio of 5 to 1, which is normally pretty good, this will be as small as 1.8%. But if you go down as low and pretty bad as 1.5 to 1, it'll jump up to as high as 5.3%. Now let me also show you there's false rejects. Again, this is where you say, nope, didn't pass. But as you can see on the x-axis, it did. And those can range from 2 to 8% over that same range of test uncertainty ratios. So what do we do about this? Well, oftentimes people will guard band, and one of the most common ones is to use the 2 sigma, which is normally twice the standard deviation. And so if you do that, watch what happens now. You can see that we've lowered the guard band. And so now what remains of false accepts is what's below the dotted line. And the good news, it's really small. It's less than 0.15%. Now, before you celebrate and said, oh, that's what we got to do, notice what else happened. If you say that everything above the dotted line fails, look at that. Over this range of at a test uncertainty ratio of 5 to 1, which again is a good one, you'd still be failing as measured. You would fail 15% of what's going through your production line. And if you were as low as 1.5, it would be 40%. Obviously, these are unacceptable. So what do? Well, you could define 4 pass-fail regions. You could say, well, there's clean passes, there's conditional passes, there's conditional fails, and what the drawing is just showing is that a portion of that measurement uncertainty is crossing the specification that you want to make. Now let me just show you how that might look in the simulation. The first clean passes, those are the same as before. And now what you see is in the region between your guard banded limit and the actual customer specification, that'll be between 2 and 5.3%. This is for this particular guard band of 2 sigma. So you can select different guard bands and you can think about these, and depending on what it is that you're trying to do, maybe you can live with that past, maybe you can't. But you can adjust the guard bands to get different values. This is one of the more common ones that's out there, so I just simply wanted to show the numbers that are associated with it. Similarly, if you say, what's the region between the actual spec and the 2 sigma, that's also 2 to 8%. So here's a table, and I've marked this as a tip that my colleague John has developed, again, for our paper. What you can look at is, by knowing simply, you don't even need to know the measured value. You just simply need to know 2 things. What's your spec and what was the uncertainty? And if you then quickly divide those 2 and come up with a test uncertainty ratio, for example, here at 4.25, that would be 2.1%. If you pass it, anywhere in the pass zone, it would be 2.1%. And if it was outside, the false reject would be 2.4%. So you can see right in this table, it's pretty easy to determine, to usable amounts of risk, what your exact situation is. Now, you're probably asking yourself, how do I optimize false accept and false reject risk? Because they're both there, and I'd like to address that. This is a chart from a paper that I did a couple years ago, and without going into too much detail, just in each case, the 4 charts on the top are false accept risk, and the 4 charts on the bottom are false reject risk. And it's 4 different decision rules. No guard band, enough guard band to produce a 2% probability of false accept, the standard deviation times 1, and the standard deviation times 2. And what you can see is that in all of these cases, I've from left to right, I'm going with no guard band to a little bit of guard band to more guard band to even more. Notice the false accept just keeps getting better but it comes at a price of increasing false reject risk. You could laugh and say it's the law of conservation of risk or whatever you want to say, but this is how it works. And I have one data point over here on the right-hand side. If 95% of your units going through your test system were passing according to just the simple rule, if you're guard banding with your acceptance of the twice the measurement expanded uncertainty, you are going to report as failing 1/3 of all the product going through. So you can see you need to really think about, and I just have the quote right out of JCGM 106 that talks about that. And so they say, acting to reduce the consumer's risk will always increase the producer's risk. That's what. So they say that in words. I'm showing it to you in solved definite integrals. So you might be thinking, well, come on, is there some way to produce both false accept and false reject? And there is. If you lower your measurement uncertainty, then you will lower at the same time both your false accept risk and your false reject risk. So how do you do that? Well, there's really two ways. If you identify the various errors in your system, and there's another instrument, maybe newer, which is more accurate than the one that you were using, that's one you can lower your measurement uncertainty right there. And there's a temporal thing with this too. So if you are there's the time at which you get the instrument and it's under, the way it was produced. And then over time, you want to make sure that it's still accurate. And that is about periodic calibration. I just want to give you an example or two here. And I also wanted to tell you a little bit of something that maybe you've never seen in a webcast from somebody from HP or Keysight. Here's the basic process that we use to develop in production. And probably the key thing that I want to tell you is once they're in final assembly and they're ready to be start electronically adjusting them and then doing final test, we make so on a RF microwave instrument, sometimes there's as many as 40 different adjustments. And what we do when we run the adjustments in production, we don't run them and say, okay, I want you to get to within 50% of the spec. We only have one adjustment procedure, and that adjustment procedure makes it go as good as it can ever go, period. It's an iterative thing. Sometimes a single spec like low-level accuracy in a signal generator takes an hour and a half just for that one adjustment. But when we're all done those adjustments, then we put them through final test. And every warranted spec in the data sheet is tested electronically. And it's only once you pass that you're done. But then you might say, pass, yeah, but are you using any guard band? So I want to show you this is what Keysight does. So you have the specification here. The data sheet specification is over here on the right. And then what we do is we guard band by that 2 sigma. So that's the 95% expanded uncertainty. And then we also guard band some more because our instruments are specified over temperature range, over humidity range, and obviously over a period of whatever the recommended cal interval is. They shouldn't drift out of that. That gives you a test line limit. So that's the limit that we use in production when you receive a new instrument. Now, for those of you that care about, is it calibrated or something like that, I just listed a few of the standards that come up most often, and I can assure you with these generous guard bands, our new instruments pass everything. Now, if someone says, well, I need documentary proof, well, then we have to run a measurement report. You might get an additional charge. But I normally recommend if you don't need that documentary proof, then that what was shown, what we tested on the final test system, is more than adequate if you can trust the Keysight reputation. But this is what we do. So perhaps you've had an impression over your career that Keysight instruments, that come from the factory are really accurate. They are. They absolutely are. I don't know what other companies do. Maybe many of them do the same thing. But I thought it was good for you to know what we do. So this is at the time that we ship it. Now, so if you can reduce your measurement uncertainty, you improve your the test uncertainty ratio, and you will reduce both those risks. Now, over time, then you have to an instrument's been in use for a while. Let's say, for example, that you're doing something where phase noise matters, and oftentimes we get the question: does it really matter to test phase noise during calibration every time? Because my third-party maintainer tells me that phase noise doesn't drift. It's part of the design. And here's my response. Yeah, it matters. It's like many other instrument characteristics. It doesn't change until it does. Here's an example. What you're looking at now is each one of these little blue crosses, or whatever they are, is a separate instrument serial number, and what you're seeing is a measure on our process flow, our process monitoring. This one happens to, now you may very well do this too, this just happens to be one in one of our calibration labs. So the spec is the red line, minus 91. Most of them are running around minus 105. So they're well below the spec, minus 105 dBc that is. This is a phase noise at 100 hertz offset. Now look what happened one day. Boom. This thing shifted 11 dB. Now it didn't go out of, it actually didn't fail, so our human technicians didn't notice this, but our process monitoring software caught it, and it turned out we were able to identify this as the source of the problem as a shift in the phase noise of the reference signal generator that was being used to make these tests. The signal generator was in a rack, it wasn't moved, and it wasn't even turned on and off. These are the little conditions that instruments really like to stay nice and stable. So once we identified that problem, we swapped it out, took it offline, put another one in, then we went back to where we were. But can you imagine if this is your system and hopefully you're doing process monitoring, but you can see that what we had done is we ate up almost all of our production margin here with this error. And obviously production margin is sacred for yield, so I want to just point that out. So how do you know that something like phase noise is being checked for calibration? Well, on our newer machines, like the one that I just showed a picture of, signal analyzers, there is no signal generator that's that good. You need a special piece of equipment, which I have shown here, and these things are like $30,000 just for one test. So when you get a calibration report, if you're the type of person or you're counting on that phase noise, then you should be getting a calibration report. And I have to say, if I don't see a report, I don't trust anything. That's like saying, trust me. I don't trust anybody. Trust but verify. So you want a report, and then you can, if you're thinking of if phase noise is important to you, look for what I'm showing in the red line. That's how you know the test was performed. And I just have a moment here before I finish, but I'd like to show you one last example of verifying the low-level power accuracy, again, as another one. So here is a cell phone repeater radio receiver transmitter. And when you go to measure receiver sensitivity, perhaps you do this, and if you don't, it's interesting in any case. What you have to do is find the minimum signal, RF level signal, with appropriate modulation that produces a target signal-to-noise ratio, or nowadays a bit error ratio. And so what's important for this is that the level that's going to occur is going to be around a microvolt, which is minus 107, or it could even be lower than that, say minus 113 at half a microvolt. So you need, when you send that signal generator in for calibration, you need it to be, the measuring receiver to be accurate. And so I just wanted to show you, if you're using, sometimes I'll see a list of equipment for calibration, and somebody's using one of our older spectrum analyzers. If you just look at the block diagrams of the one that we're recommending with the lower uncertainty here, this is the PXA or PSA, either one of those. Those errors down at minus 107 are going to be as low as 0.2 dB. And I showed generously that it's greater than 1.5. It's actually worse than that. And that's because there's analog filters, analog steps of gain, and worst of all, analog log amplifiers. And now this is all in a custom ASIC. So here's the situation. If you were looking at a measurement, the spec of a signal generator like that is plus or minus 0.8, and you see with the plus or minus 0.2, how nice that is. You can be very confident that, yeah, that instrument is really in spec. Let me just show you what it looks like for that older instrument. So here's the last tip that I want to give you, which is, if one of your sources of error is, say, in a signal analyzer, you may very well be able to dramatically improve that error source by getting one of the new spectrum analyzers. And in many cases, if you talk with your field engineer, they can provide a trade-in credit for some of those old ones. If I had your jobs and I was using one of those older machines with analog IFs, I would pound the door until somebody allowed me to get one of the new ones with the digital IFs. They're that good. And this was just, I'm not really going to have time to explain this, but I just want to say, we actually have, some of our application engineers can do a whole analysis, and I did an analysis in this case, at this signal level, of if you had an uncertainty of 1 dB versus 0.2, then your actual false failures could be reduced from 12% to well under 4. So with that, I'd like to conclude, and this is really what I'd like to tell you. Hopefully, I've reminded you that all measurements contain errors, and therefore it's important to estimate the sources of error and determine your system accuracy, or as we've said today, measurement uncertainty. Then the next step is, how much false pass or false reject risk can you live with? And that'll be different for every company, every organization, and perhaps different departments. But based on that, you can then select a decision rule that has appropriate guardband to achieve your % risk tolerance. And then finally, as time goes on, make sure that when you're doing, when you send your instruments in for regular calibration, that you're getting very accurate measurements from them, and that their test uncertainty ratios are really good too.